Awesome. Yeah, so this will kind of like be more continuation from like, well, really section 32. Last time we talked about like the white noise model and what else? Walking or random walk with a drift, right? So I'm just gonna quickly review that, and then we'll talk about autoregressive, moving average, and then combining them together essentially. So let me go ahead and I'll share my screen. Here we are. Okay, and there you guys are. Cool. Awesome. All right. So I can still see you guys. All right. So let's see here. I'm just making an update, or where were we? Stats, statistical modeling. Oh, so one thing too, if you go on the repo, okay, and I see Hazel and Tara came in. Awesome. On the repo, I haven't done this yet for everything, but I'll just give you guys a little sneak peek. Is that I'm making it so that it's a little bit easier to follow like which module and section and which like notebook I have in here. So if you guys, I don't know if any of you guys actually use the notebooks outside of the study groups, but if you want to look at the study groups or the notebooks from the study groups particularly, I'm trying to organize it. So this is just for module 3, but I'm hoping to put it for the rest of the modules like module 4. So no, that's gonna come in there. Hopefully you'll find it a little bit easier to find these parts because I have a hard time too. All right, so I want to look at models basic. So this is what we talked about last time. Is our white noise model and our random walk. Just to kind of review really quickly, remember our white noise, essentially, it's just randomness. There's no correlation between time. Essentially, it's just picking, in this case, I picked a random distribution around the normal curve. You could modify this slightly, right, to like have a different kind of randomness. But for the most part, usually you would do a normal distribution for a certain average and then the standard deviation, right? And then go from there. And then from that, essentially, I can make, oh, I guess I didn't run this already. So let's just kind of quickly just run it so you reminder. So this white noise model, essentially, it's more or less, you know, like noise. You can see like, I think the average was 10. Yeah. So you see the average is 10. It's hovering around 10, but there's no like specific like time dependence. So you don't see it going up, you don't see it going down. If I pick, you know, if I get 14 or 15, it can be just as easily be like 6 or whatever. It doesn't have to be like built on there. Different from the random walk model, which is closer to kind of like what I think most reality really works like for when we talk about time series, is that the previous like period or the previous data point should have some effect on the next data point. So essentially what it is that we still have some randomness in there. That's what this epsilon t represents here. And that will usually be represented with a white noise model. But essentially it means that we have the previous value, which is yt, the y is the value, right? So y of t minus 1, so yesterday's value or whatever period of time before, plus some noise essentially. And when we do that, we see that we have something a little more, you can see between each individual day, it kind of staggers, but you'll actually have more of like, as you're going down, you tend to be closer to that down part. So it takes a lot of effort to go up here. So you can imagine like flipping a coin over and over again. Note by this chance, we started at 0 and the standard deviation was 10. If I had more points, let's see if I can do this real quickly. If I had more points, this might extend further out. So if I do this again, we can see here, in this case, it started off very low at like 1500 and then it started moving up and up and up and up here. And then of course, if I extend it even further, let's say 75, we might see it kind of average out going back down. For the most part, this is just completely random. This should in the long term go to 0 because you have random fluctuations up and down. Okay, cool. And then the last one, random walk with a drift, which basically is the same thing here. I try to show a good example of like, if I had many, many values, you would expect it to be, so you can go up and then it goes back down again. But random walk with a drift is the same idea here. However, what's going on here is that you're actually adding in an extra term, and this here term C right here, every single time. So essentially you drift towards that C, or C is basically pushing it towards this. I think last time talked about like random walk being like a drunken person, like going back and forth, you know, they might take a step to the left, they might step to the right, you know, and they go back and forth, but there's not like, like where they are in the room depends on where they were previously, but they could go left to right just randomly. Drift is kind of like the same drunken person, like, you know, walking back and forth, but there's like a wind or something like that, like some wind that's blowing them constantly off to the side. So they might go left, they might go right, but they're always being pushed off to the left. So you can see here, there's C.5, and you'll see, I think I graph each point on here. Again, this is just review. You can see here's what this generally looks like for up to those values. You can see it going to negative. But with the C, which is always basically that adding that little drift of C, it pushes up further and further. Note that if the value is smaller, the drift is smaller. Okay, cool. Sound all good? Any questions on this review? Okay, cool. So I want to kind of just, you can see here is that basically we built up from the white noise model, and then we ended up getting a random walk, and then that C part ended up a random walk with a drift. So you can see we can kind of like add these together to make new models. That's essentially what's going to happen with our, different autoregressive model and our moving average model. So kind of looking at this, again, this is from section 32. So just kind of reviewing, and you can see some similarity here. So our autoregressive model, or AR model, right? You can see the formula here, which is our current value, is equal to some value. So you can imagine that like a drift. So that mu right there is a certain number, right? That is the number that is our average essentially. And then plus this psi, right? So, or not psi, no, this is psi. Sorry, no, phi. I don't know. I never knew which one to say it as, but lowercase phi here times the previous value plus the white noise, right? So what this means is that it's still dependent on the previous value, but this phi right here is going to modify the previous value. So you can see, for example, if phi is equal to 0, essentially we have the white noise model with a mean of mu, because basically all we have is the white noise model. 0 right here, basically the previous value doesn't count. And then plus some mu, basically it's always going to have a value, right? It's going to increase. But mu less than 0, which is kind of interesting, is that it will actually oscillate. So essentially what will happen is that if you imagine this being like negative, if your previous value was 10, well, then it's going to be minus 10 plus, some white noise. So you'll tend to get smaller and smaller and smaller until you get on the other end of like 0. And then basically it'll flip over and go the other direction. So you tend to have this oscillation factor. Note that there's still some noise there, so it's not super easy to see where that oscillation comes from, but the stronger or the more negative this is, the more essentially power this will have from the previous point. Basically, it's pointing in the opposite direction of the previous day. And then we can see phi greater than 0. Basically, previous points are correlated, positively correlated with the past. So this is what we call autocorrelation. So essentially it means that, oh, what happened in the past matters. Okay, makes sense to everyone? Any questions on how this equation is similar to what we've seen already? No? Okay, so a good example of this is just start coding it up. So you can see I already put a few phi here so we can kind of play around with it. But you can see we'll have an average of 0 just to make it nice and simple. We're going to ignore that mu essentially for now. I think I ignore that, yeah. And then standard deviation of 4, a number of points. I'm going to start with 100 just to make it easier to see. So I'm sorry, I do put a mu here. So I will keep it there. But this is basically this is going to be from our white noise model itself, okay? And we have our phi of 0.1, so we should be in this domain where we should have some autocorrelation, and then we'll generate some points. We'll generate this part. We've kind of seen something similar already, where essentially we're just doing a for loop over and over and over again, right? This is not the most efficient thing, but it'll be all right for here, okay? And then we'll go and plot it out. So when I run this right here, you can see this is basically our time series, and it's a little not, I don't know if you guys can see it. I don't see any particular like thing that makes it like, oh, clearly this is having some autocorrelation in some way. But you can maybe see there's a little bit of pattern in here where the previous point, but for the most part, 7.5, don't see that much difference. So let's see here. So let's increase this phi up some, right? So let's do 0.09. So you can see here, now what's happening is that the previous point with a larger phi here, basically the previous point really matters on what the next point will be. So even though there is some randomness going on here, essentially, if you're already positive here, you'll tend to keep going positive, positive, positive. And you can see there's going to be a higher and higher value going up. Does that make sense to people? Cool. Thumbs up if it sounds good so far. Sideways, you're like, I don't know what's going on. Okay, I see mostly thumbs up. And then I know Hazel and Tara, you guys are cameras off, so if you have a question, you can put on Zoom too, on the chat. But okay, and then let's try out with a negative value. So let's try like -5. So this one right here basically means that if we have a value, it's going to want to push it down. So essentially, if we get larger values, like imagine if we had our previous value was like almost 70, right? It's going to subtract 70 from the next one. So you'll tend to see it's going up and down, up and down. So if we do this now, you can see more fluctuation going up and down here. If I had a smaller negative value, you might see a little bit like it's able to kind of get past a certain point. And then I believe if I have a large enough phi value, you can see a lot of oscillations. You can really clearly see there's oscillating right around here. Okay, and that's because basically last point matter, like yesterday's point really matters, but it's going to subtract each one. So if you have a high point here, we're going to get minus 20 plus some randomness and get the next point. You know, this was negative. Well, negative times a negative, right? It's positive. So it would go up really high and up, down, up, down, up, and down, down. Okay, cool. All right, and that is our autoregressive model. And the reason why we call it autoregressive essentially is that it's dependent on the previous point. Essentially, this phi times yt minus 1, remember t minus 1 is the previous point, it basically says, oh, that's the part that matters. And this is kind of similar. This is actually what we talk about with autocorrelation. Okay, cool. So I'll move on to the next one. Sound good? All right. So the next one is our moving average model. So now this is very similar, but it's a slightly different thing. So what's happening here is that we still have some time dependence, but this time dependence is actually going to be built on the actual previous noise value. So it's not necessarily the value itself that we ended up with, which is yt or yt minus 1. We're actually going to have epsilon t minus 1. So epsilon t minus 1, remember, is a random noise that we have, and that random noise will be basically bumped up by theta here. So you can see a very similar structure right here, but note that it's just basically the random noise right here, or in this case, it's going to be a white noise model. So note that if we basically get rid of 0, essentially it becomes the white noise model, right? If we have less than 0, we have an oscillation, right? So basically the previous point is going to be the reverse of this. And then if theta is greater than 0, we're going to have things that are correlated with the past, which gives us autocorrelation. Okay. So just running the same thing, and you can see the biggest difference here is that essentially I'm keeping in fact that there's epsilon I here, and I get epsilon I plus 1. So that way we're kind of adding this all together. And let's go ahead and run this guy. So you can see we had a theta of negative 0.05. So you can see there's a little bit of oscillation here. If I do, let's see, this sometimes can be kind of tough to see because depending on the, what's it called? The noise, if the noise is very strong, you might see more of an effect. So we'll see what happens with negative 0.09. And you can see here's a little more oscillation. I don't know if I can make this that much higher if you can see anything better. It might overpower it. Yeah, not that much. Okay. I'm trying to make it so it's like really obvious. But you can start seeing like there's definitely some oscillation here, right? And then if we have more positive, let's get rid of this guy. Okay, so we have something a little more positive. You can basically have more autocorrelation where you can see it's not really oscillation, but you can see that the previous points are more likely to stay at a high point to begin with. But note that it's still based off of the noise itself. So note that basically if we tend to go downward, well, that means we're going to continue going downward. If we're going upward, we're going to tend to continue upward. But there's still points where we can have an inflection where you can see if we go down and then back up again. Okay. If we have this very strong, basically the noise overpowers everything, right? So if I make this really, really strong, you can start seeing basically it becomes really noisy because essentially it's built on the previous noise point. Okay, cool. Any questions? No? How are we feeling with this? Thumbs up, thumbs down, sideways? Okay, I think I see some head nods. Most part. Okay, so a couple had thumbs up. Okay, cool. So yeah, so these are our two big models. So you'll see like, well, okay, like these are very similar, but the biggest difference is this portion and this portion. And then the next part is saying, okay, let's put them together. Let's try to see if we can basically have some dependence on the noise and dependence on the previous point, right? So that gives us into our ARMA model, all right? And so you can see here is that essentially what we have is just those two equations squished together. So we still have that mu plus that little noise, right? And then plus basically a part that's dependent on the previous point, you know, and then our plus our previous noise point. So what's kind of cool though is that also the next thing to ask is, well, okay, we have this from the previous point. Anything else that we can kind of like modify from this equation that you might think about? What things could be like changed in here? So I'll give you a hint. What's the one number that's in here in this formula?
1.
1, right? So then you start asking yourself, does it have to be 1? Like, what does 1 represent? Well, -1 just means it's in the past. What if we had -2? Or, 10 days ago, or 12 days ago, or whatever your time, period is, like, whatever your frequency is. Like, we could have something where it's dependent on the previous year. Maybe, for example, I'm trying to think of a good analogy here, but like, if you had something that was, you planted like a seed or something like that. Imagine it that way. It's like you planted a seed, it's going to take 12 months or however long it takes for, I don't know, I'm not a gardener, but however long it takes for, plants to grow, right? You would see a result afterwards. That's essentially what this, minus part here. So that's what we talked about higher order. So you can see here, ARMA 2, 1 essentially says, okay, like don't just consider the previous, like just the previous point, consider 2 points ago. So -2 here. And then you can see 1 is representing basically the moving average part. So for the moving average, only look at 1 here. What would, anyone got to guess what, if I had, let's say, ARMA of 3, 4, what would that look like? Maybe I'll start simple then. 3, 1. Let me ask, what's the one number that would change if I changed it 3, 1 from ARM 2, 1?
3.
Yeah, 3, right? So, and what's the one number that we would change it from? So we're changing some number to 3. What number are we changing in this case?
2.
2, right? Yeah. So essentially what this would mean is that it would be the same thing, but in this case, I will change this to -3. And note that I put this _2 here. That's just saying it's, oh, this factor belongs to here. So I might change it to this way. But note that you can also have multiple orders. So maybe it's not just dependent on 3 days ago. You could later on, add in other factors, something along the lines of, let's see, you could have something where it's like, okay, well, not just 3 days ago, but also -2 days ago. You can see this part. So this is be something you're building up further and further. And this would be higher order models essentially being added up together to basically say, okay, well, not just 3 days ago has an effect, but maybe 2 days ago has a different kind of effect. This is where we can talk about like, PACF and ACF, our partial autocorrelation function or autocorrelation function, saying, what things have an effect here. But the point is that you can basically add these features together, well, these time periods before, and add those as part of your model to say how it's dependent on the previous point. Okay, cool. Any questions coming off of this? Whether I got this equation, or how you can modify this equation more, or how this is useful? No? Okay. One thing I do want to note about this one, it's kind of interesting if you look at this carefully. If I enchain, I'm going to go ahead and copy this cell. So let's say I go ahead and change this guy. So if I change this over to something like, let's say 3 times x _ 2. I'm using x because I'm trying to be trying to lead you guys on a little bit. Okay, and I'm just gonna get rid of this part just so you don't have to worry about it. All right, well, yeah, we'll just go rid of this part. So looking at this equation here, what does this kind of look like to you guys? Does this suggest anything to anyone? It's something we've seen really early on.
Linear regression equation.
Yeah, good. Linear regression equation. Thank you, Jared. Yeah, and essentially that's what we're doing when we're doing like these time series. Essentially what we're doing, we're making linear regression, but our features are not just like, other features. Our features are literally the time point, like points in time. So that's how you can really think of like a time series, is that it's really a linear regression, but based around time. So I think that's kind of a nice thing to know, because then you're like, oh, well, we've done linear regressions. We've learned a whole bunch about a linear regression. This is why, for example, we learned about extensions of linear regression, logistic regression, which basically came off of linear regression. And now we have time series. They're basically all related in this way. Cool. All right, awesome. All right, so I'll go ahead and stop the recording here because I don't have any more to talk about for this particular modeling, and then we'll go into questions. Sound cool?